Hi, I will introduce a special method and a deeper breakdown for this method. In this question, what's the outcome we want to find? Take this outcome as an example. If we have 4 dots, 4 points, then we can draw a semicircle like this. It contains all the points. Or we can draw a semicircle like this. Or we can draw a semicircle like this. There are semicircles containing all the points, and this is one of the outcomes we want to find. How about this outcome? In this outcome, we never find a semicircle containing all the points, right? It's impossible. And I found a very special and magical solution for this question from another YouTube video. That is this, and I will share the link below the description so you can check it out. But in that video, I found myself and so many other viewers are not satisfied with the explanation. So I want to give you a deeper breakdown for this method. Is if we have a point, for example, if we have this point, then we try to give it a corresponding diameter, and then we have a corresponding semicircle. So 1 point, 1 corresponding diameter, 1 corresponding semicircle. And why we want to do this? Because if we have any other point, for example, like this, we generate a diameter in the same way. And then we also generate a corresponding semicircle in the same way. And then what happened? For this second point, we have this semicircle area. And for this first point, we have this semicircle area. So now we can see a overlapped area here, right? How this overlap area looks like doesn't matter. What matters is if we can find any of this overlapped area by all the points. It should be overlapped by all the points. So how about we have 3 points? Now we have 1 point, 2 points, 3 points, and then we do the same thing. And then we have a corresponding semicircle. And what you can see is you can find a overlap area in this shape, right? So this shows that we can find semicircles that contains all the points in this case. So how about we try another case? This, and this. So we do the same thing. And what happened with this case, with this outcome? As you can see, you cannot find an overlap area by all the points. There is no area overlapped by all the points. Okay? There are only areas overlapped by 2 of them, not all of them. What we want is all of them, right? Because the question is of n random points. So what we want is we want semicircles to contain all of the points, not some of them. So in this case, this is not the outcome that we want. So now we transform the original question into this new one. If we have n random points, then we have n random diameter, right? So we draw a random diameter. For this example, the n is 3. The n is 3. We draw a random diameter, and then how many possible combinations can we get? For each diameter, we have two possible place, right? For this diameter, we could have this place, or we have this place. For every diameter, we have two possible place corresponding points, right? So now we have 3 diameters. So the total combinations is 2 power of n, and now n is 3. And how many possible overlapped area? Is 1, 2, 3, 4, 5, 6. It's the all possible overlap area for all the dots. And in this case, all the dots is 3 dots. It's 3 points, right? So it's 6. But how can we generate this 6? How can we generate this 6? It's by the number of radii. 1 radii, 1. 2 radii, 2. 3 radii, 3. 4 radii, 4. 5 radii, 5. 6 radii, 6. So we generate this 6 by the number of radii. Then the number of radii is 2 times of number of diameter, right? This is basic, and as you can call. So the answer is this. The answer is this. Now we put 3 into this n, and now we can get 6/8. So it equals to 3/4. So this is the answer for n equals to 3. Work. It's a little bit unbelievable. So I try to make it more convincing. Is now let us imagine a simple experiment. In this experiment, we can have some outcomes, and the all possible outcomes is in a sample space, and it's 1 to 9. And now how about we sort all the outcome into 2 kinds of events. 2 kinds of events. The one is event odd, the other is event even. So in the event odd, we have 1, 3, 5, 7, 9. In event even, we have 2, 4, 6, 8, right? Okay, so here is the same. Here is the same. We have a sample space for this question, for our question. The sample space, inside the sample space, there are infinite possible outcomes, right? And in this video, we call them point combinations. So the point combinations is infinite. It could be this, it could be this, it could be this, it could be this, and so on and so on. Okay? And think about this. We also have infinite events that in this video we call them diameter combinations. Diameter combinations. It could be this, and also it's infinite. There are so many possible combinations out there. All right. So think about this. We can pick just one of them from this events set, and we call this one event A, and also we can call this one event B, event C, event D, whatever. And now we try to understand this event A. It is an event A. In this event A, we have these diameter combinations, and that's it. And now what you can see in this diameter combination, for this diameter, there are 2 possible corresponding points. right? And for this diameter, there are 2 possible corresponding points. And for this diameter, also there are 2 possible corresponding points. And now, how many point combinations belong to this event A? How many? You can try to enumerate all of the combinations, but I just give you a quick example. Like for this red one, we can pick this. For this blue one, we can pick this. For this green one, we can pick this. All right. So the all combination is 2 multiplied 2 multiplied 2, right? And we do it 3 times because now the case is n equals to 3. All right. So basically, the whole point combinations that belong to event A is 2 power of n. And now, how many kinds of overlap areas that we can find? It's 1, 2, 3, 4, 5, 6, right? And basically, I already explained, it's the number of radii. It's a number of radii. So it's 2 number of diameters, and it's 2 times of number of points also. So this is the answer. So now, for every event, this is event A, and we could have another event. This is event B, for example. And now, like this, we can see this in a bigger picture. Event A, event B, event C, event D, event E, event F. And what do you think? What do you think the probability distribution for all the events in this set is even, right? Every event have the same probability to happen. It's even. And every event, each event has corresponding point combinations. It could be like this, like this, like this, like this, corresponding point combinations. All right, it's like what we do from this simple example. All right, this 1, 3, 5, 7, 9 belongs to event R. This 2, 4, 6, 8 belong to this event even. So now we do the same thing. We have the same thing. Some of them belongs to this, and some of them belongs to this, some of them belongs to this, and so on and so on. But inside just one event, there are some point combinations that don't have any overlapped area, like what we explained here. Not all the point combinations have overlapped area, right? Some of them don't, some of them has, right? And we only have 2 times of n of the point combinations that have overlapped area. So this is the bigger picture for this magical method. And I hope this can make more people understand this wonderful method. And that's it. Let me know if you have doubts in comment. I will try my best to answer. Thank you.